Thank you all for joining us for the last session for today. And each of the so the way we're going to do this is we're going to have about 5 minutes for the actual presentation. To all presenters, I will signal with, I will raise my hand when you're at the 5-minute mark, and I will raise my hand again 30 seconds afterwards. So let's try and stay on time. And we will also have 2 minutes at the end of each presentation to allow for questions from the attendees. So with that, let's get started with our first lightning talk of today, which is going to be on benign overfitting of binary classification using Gaussian mixtures by Wang. Kay, would you mind sharing your screen? We can test if it works.
Yeah, thanks, Vidya. Actually, I seems okay. I see. I can share. So can you see my screen?
I can see it.
Okay. Can you see the move? Like. Okay. Thank you.
Kay.
Yeah. Thanks, Vidya. So hello everyone. I'm Wang from UC Santa Barbara. I'm glad to be here. The topic of the talk today is benign overfitting in binary classification of Gaussian mixtures. This is a joint work with Christos Thrampoulidis from University of British Columbia. So let's still start from background and motivation so we can see how our work is related to others. We know deep neural networks generalize well despite over-parameterized. As shown in this plot, we can see the test error decreases again as the model gets larger, even if the training error is 0. This phenomenon is called double descent, as have been observed by those works. To study the principle behind this phenomenon, some works focus on linear regression in both asymptotic and non-asymptotic settings. And actually, Peter Barley gave a talk on this earlier today. Compared to linear regression, the study of classification can be more challenging. And one reason is that one commonly used classifier, SVM, the support vector machine, doesn't have a closed form expression. Motivated by that, Vidya et al.'s work study the link between SVM solution and the least square estimator. They study the discriminant model, such as logistic regression and the sign model. Different from them, our work focuses on Gaussian mixture models, which is a generative model. We will see that this extension is not trivial. Okay, so Gaussian mixture model is defined as this. We have the label Y, and the conditional on the label X follows multivariate Gaussian distribution with mean Y times eta and the covariance sigma. The question is, when does benign overfitting occur? So here, benign overfitting means that the classification error approaches 0 as p goes to infinity. So we first study the link between SVM and the least square estimator. By Sodry's work, we know when the data can be linearly separable. If we start from 0 and run gradient descent using the logistic loss, then the iterates will converge to the hard margin SVM solution defined as here. If we run gradient descent using the square loss with the same assumption, then the solution, then the iterates will converge to the mean norm interpolation solution. We can see the difference that here for the interpolation solution, we have equality, but for the SVM, we have inequality. And we know the interpolation solution has a closed form, which is this. So it can be easier to study the interpolation solution. And the theorem 1 actually states the connection between SVM and the least square estimator. When the covariance is identity, then the SVM solution is the same as the least square solution with high probability. In other words, like the SVM solution interpolate data with high probability if those two conditions can be satisfied. The first condition requires that the number of features P is large enough compared to the number of observations N. Okay. The second condition requires that the norm of the mean vector eta cannot be large compared to P. The second condition is specific to the Gaussian mixture model. Because for the sign model, it only requires the first condition, doesn't have the second condition. We also run numerical experiments to verify our result. Here, those two plots shows the fraction of support vectors. We can see after rescaling the x-axis using our result, those three lines overlap. Actually, we have more results in our paper. We derive non-asymptotic upper bounds for the classification error of the LS estimator. Then combine the upper bound with theorem 1 introduced before, we derive sufficient conditions for benign overfitting. In our new work, we also extend this result to asymptotic settings, and we also discuss the role of regularization. And finally, I introduce briefly about the proof. Okay, we show that it turns out that we need to bound quadratic forms of this. The challenge is that X, which is defined here, includes Y. So to characterize the dependence, we consider this quadratic form as a whole by applying the Woodbury matrix inverse identity. Please see our manuscript for more detail. Thank you so much for the attention.
Thank you very much, Kate. That was great to hear about. And do we have any questions from the audience? Okay. I have one question for Kay, actually.
Yeah.
Can you say a little bit about how much more difficult the anisotropic analysis is relative to the isotropic case? So I can see how the proof highlight would work here for the isotropic case, but I'm not entirely seeing it for the anisotropic case.
Yeah, that's a very good question. And the first difficulty is here. If we look at this, for the isotropic case can simplify, this term a little bit. That's the first challenging for the anisotropic case. The other difficulty is that here, all the eigenvalues of sigma are the same, but for the anisotropic case, they are different. If some eigenvalues are much bigger than others, then we need to separate those big eigenvalues with others. That's another challenge for the anisotropic case.
Cool. Thank you. Thank you very much, Key, again. That was a very nice start. So next up, we will have label-imbalanced and group-sensitive classification under overparameterization. And I believe our presenter will be Ganesh Kini.
Yeah, thank you. I believe my screen is visible with you. Okay. Yeah. Hi everyone. I'm Ganesh from UC Santa Barbara. So in this talk, I'll give a lightning overview of our recent work on label-imbalanced and group-sensitive classification under overparameterization. This is joint work with Orestis, Samet, and Christos. Well, in the interest of time, we will restrict the focus of this talk to only class imbalance. However, our work extends to group imbalance as well. So in standard classification problems, typically the goal is to minimize the misclassification error on the test data. But in the presence of label imbalance, we are often interested in a more equitable quantity called the balanced error, which is basically a simple average of the class conditionals. A standard learning strategy is to employ empirical risk minimization with a suitable loss function. Cross entropy, though, is known to hurt the minority classes. Therefore, a natural modification is to use a weighted cross entropy loss. However, this does not work in the over-parameterized regime. And this is important to us as modern architectures are often over-parameterized. There have been several recent efforts to fix this shortcoming by using additive adjustments to the logits, which we will refer to as the LA loss. However, we show in a concrete linear setting that LA loss is also ineffective under overparameterization. So as a fix, we propose a new loss function that instead of the additive offsets, scales the logits with label-dependent multiplicative factors, delta y, and we call this the vector scaling loss or VS loss. So let's just pause to summarize a few key results. So in over-parameterized linear classifiers, the LA loss does not improve the balanced error. We show that the VS loss does. In fact, in linear classifiers, VS loss can be theoretically shown to outperform the LA loss. And as a proof of concept, we give experiments on real-world datasets with both linear and nonlinear classifiers. Without going into too many details, this is the reason for LA loss not improving the balanced error in overparameterization. Let me just briefly state our claim that if you obtain a linear classifier on separable data, the direction of the resulting classifier will be the same as that of the standard SVM, irrespective of any finite choice of the additive adjustment parameter iota. Now, complementary to the previous claim, in the same setting, we prove that the VS loss gives us a classifier that is aligned with something different from the standard SVM, something called as the cost-sensitive SVM. This is the explicit connection that we make of the VS loss to the CSSVM. So on linearly separable data, the hard margin CSSVM results in a linear separator that achieves different margins to the two classes. That is based on this parameter delta. Here is an experimental result with a linear classifier showing how LA loss and weighted cross entropy perform identically as a standard SVM in the overparameterized setting for any choice of the additive adjustments or the weights. Whereas in contrast, the VS loss outperforms them both in balanced error with a controlled trade-off with misclassification. To give a brief glance of the performance of VS loss on real data, here are two sets of results. The first is from training a linear classifier with VS loss and LA loss on binarized MNIST label-imbalanced classification. We can note here that VS loss firstly outperforms LA loss, and also that both these are consistent with the corresponding SVM solutions, that is SVM and CSSVM respectively, that they were shown to converge to. Another experiment is on multi-class classification of MNIST with the Lenet architecture. The multi-class extension to VS loss gives lower balanced error compared to cross entropy and LA loss here as well. In addition, we also have experiments with group imbalance, but whose details we won't go into in this talk. Finally, in our preprint paper, we have several other details, which we invite all of you to see. We think that there are several really exciting future directions. Well, one of them is to try and better understand the benefits and dynamics of the vector scaling loss in non-linear learning models. So with that, I would like to thank all of you for listening, and thanks for organizing this great workshop.
Thank you very much, Ganesh. That was a great talk. Do we have any questions from the audience? If so, please raise your hand. So Ganesh, I just had one very, Parthe Pandit, perfect. Just a hand, raise his hand.
Hi, great talk. How does delta y relate to the imbalance between the classes?
So the choice can, so it's a hyperparameter that we can choose. So one intuitive way of choosing delta is to, look at the class, the imbalance ratio, that is the class priors. And say one intuitive choice is to just make it inversely proportional to the class priors or some power of the class prior. So in general, in our preprint, at least for the Gaussian mixture data with linear classifiers, we outline a method to tune the delta parameter to optimize this balanced error, at least in GMM settings. And also that leads to another heuristic that can be used for GMM-like settings.
Thanks.
Perfect. Thank you again, Ganesh. And we're going to go ahead to right ahead to our next presentation, which is margin distribution. Are all data equal? And this is going to be presented by Andrzej.
Andy Banburski works. Okay, excellent, thank you. Welcome to this talk. I'm Andy Banburski, and I'm a postdoc at the Center of Brains, Minds, and Machines at MIT. And this is work done in collaboration with a lot of great people. And it's going to be a bit different than other talks because it's going to be more experimental and phenomenological. And it's going to answer the question that's probably on everyone's mind now, which is, are all data equal, or are some data more equal than others? So a little bit of motivation. There's this developing story in the theory of over-parameterized networks that seems to suggest that, at least for networks trained on cross-entropy laws, stochastic gradient descent seems to have this implicit bias that leads your networks to train towards a solution that maximizes classification margin. And there's a body of work that has been pointing in this direction, and there's going to be also a talk by Tommy Poggia tomorrow, which will talk about this in the square laws. But maybe, so we know that margin seems to be maximized. Is there a connection between this margin maximization and some kind of guarantees about good performance on the test set? Could we use the information about the margin distribution over the whole training set and somehow rank different minima of a given architecture? Or is this not something that's possible? Well, there is this recently discovered neural collapse, which suggests that asymptotically, actually what happens is that the whole margin distribution becomes flat. And so somehow there would be very minimal amount of information there. But what about finite times? We can kind of plot the distribution of margins for an over-parameterized network that has been trained past 100% training accuracy. And you can plot what happens to the margins for every data point in the data set. Let's say that this is CFAR10. I have 50,000 data points. I can plot and sort the margins of the whole data set and plot this over time. We find that indeed this thing becomes flatter, but it is not flat. It has a few data points that are really small margins, kind of like support vectors, and some number of data points that have really large margins. So this is what we kind of find experimentally. And you might then try to do the same thing for many minima in the same network. You initialize it many times, and you find minima to do better and do worse. And we find that the ones that do better have a higher margin curve, if you wish. This margin curve nicely correlates with the fact that the higher it is, the better the test performance. Meaning the area under the curve, the bigger it is, the better the test error. And this is kind of an obvious one. But an interesting observation here is also that the number of the data points that are kind of on the left part of this margin distribution, the ones that have the smallest margin, the kind of support vectors, the less of them you have, the better you also do on the test. So this does seem to suggest that small margin data are more important than others. But how much more important are they? And which ones are they exactly? Can you find them? So how would you go about doing this? One way you can do is you can try to compress the data set bit by bit and see whether we can discover these data points. So let's say that we train our over-parameterized network to 100% training accuracy. You keep training it for a while, and it's more or less stabilized. And you keep training by gradient descent, but now you're going to start throwing out data points from your training data set. And you start gradually cutting your data set down from 50,000 data points to 40,000, 30,000, and so on. And we find that even when we go down to 100 data points through this procedure, continuously trying to hit training accuracy to be 100% all the time, at 100 data points, you lose about 1% of accuracy. And you keep going, and you find that the minimum that has better test performance originally is the one that you can kind of compress more. the one that had worse test performance, you can compress less. This is an interesting observation here. This is not exactly a practical argument, but you see that eventually, let's say the 20 data points that are the support vectors eventually, the ones that had the smallest margins, are completely different for these two different minima. So this does seem to correlate that at least these small margin data points, which ones the network focuses on, lead to different test performances. You can also, instead of doing this compression bit by bit, compress all at once. I can train my network to 100% training accuracy. The moment I hit this data separation, I can throw out everything from the 50,000 apart from the top 100 or top 200 data points. And by top, I mean the ones that have smallest margins. And we find that you lose a little bit of test performance, but you lose a minuscule amount. And if you do a hyperparameter tuning and kind of search over the space of hyperparameters, you find that on different architectures, you can go down to losing only 0.1, 0.2% of accuracy on the test set by going down to 0.4% of the original data set. So really, it seems like the network doesn't really care about all of this data. And interestingly enough, we do find that different optimization algorithms throughout this procedure lead to different results. In the case of SGD, the smaller the change in test error, the original, you had also some better test performance. So it seems that more stable networks are better performing in general, but this is not the case for Adam. So this does maybe kind of put this direction that the different optimization algorithms might be converging to different implicit bias, leading to different behavior in this kind of compression sense. The question now I asked was, can we predict which data these are? So let's say that I initialize two different networks and I initialize them at the same scale, that they eventually converge to a solution that performs more or less the same on the test set. They have the same test accuracy. Would they have the same data points that are kind of supporting them? And we find there's a plot on the left here of two different networks that more or less perform the same. They end up converging to let's say these 200 data points that are important. Only 60% of them have overlap between the two different networks. You can repeat the same experiment on 100 different networks, and you have this histogram on the right, and you find that on average, they share maybe 50 to 60% of the data points that are the smallest margin. All the other ones are different. This really does seem to suggest that, kind of to summarize, you can compress your data set, but this compression is highly dependent on the initialization and the randomness of the initialization. The network, when it converges to the things that matter to it the most, it converges to something that, as I mentioned, only a few data points seem to matter to this network, but which ones they are is not really something that we can predict, and is highly variable by different training runs. This also probably implies that the high capacity features that the network learns for classification are also random and inconsistent between runs. I guess this is more or less maybe a good place to stop. The one question that maybe I will pose to the audience to kind of push you is, why would small batch size and large learning rate on these plots that we had previously seem to be better for compression? Is this maybe suggesting something that with small batch SGD is easier to find global minima, or maybe there's some other explanations? I'll stop here. Thank you.
Okay, thank you very much, Andy. And I think if anyone has maybe a quick question, we can take it now. Otherwise, we can move on to the next speaker. Okay, why don't we go ahead to the next presentation, which is deep learning generalization, extrapolation, and overparameterization. And this should be by Roosbe.
Hi, yes. I hope you can see my slides now. Okay. Hi, everyone. My name is Rusbe. My talk is about deep learning generalization, extrapolation, and overparameterization. I'm going to try to connect all of these three pieces together. So I've summarized the work in 4 messages. Message 1 is that the functional task of a deep learning image classifier is extrapolation to a moderate degree outside the convex hull of what it sees during training. So what we see is that testing samples are outside the convex hull of training sets in the pixel space and in the representations learned by deep networks. What we see is that there is no evidence that the deep network is interpolating in any of its inner layers or in the pixel space, or even when we extract features from images with wavelets or shearlets, or even when we pick a subset of those such coefficients, we see that the convex hull of training set is not large enough to contain a testing or a validation set. And this of course can be explained partly by the high dimensional space, but we see that even for a ResNet model, the last layer, layer after the last pooling layer, like it has only 64 dimensions. And in that 64 dimensional space, still all the testing samples fall outside the convex hull of the training set. So in that time, the distance to the convex hull is significant compared to the size of the convex hull also. So this is in that 64 dimensional space after the last pooling layer of a ResNet model, ResNet 50 for CFAR10, we see that the distances have this kind of a distribution, and their distance is not negligible. We can't dismiss that as it's a small distance. And for an image to arrive at the convex hull of a training set, it has to change significantly visually, as we see here. And the change in the image, changes in the image has to do with the object of interest in the image as well. This is true for the MNIST as well, handwritten digits, and also we have seen it for some medical image data sets. So let me focus on the word extrapolation here. And by extrapolation, we mean going outside the convex hull, but within the scope of the training set. So we don't imply that like we train a model on handwritten digits and the model goes on to extrapolate and classify tumors in radiology images. That's not the meaning of extrapolation we imply here. We mean extrapolating within the scope defined by the training set. And as it happens, this definition is used in cognitive science papers. So this image shows a simple example. We have these 3 shapes in the middle, and if we extrapolate on the right-hand side, we arrive at this shape, and extrapolate on the left-hand side, we arrive at this shape. This is extrapolation, but within a specific task, within a specific scope. And it's quite different than going out of distribution. But as it happens, the distance to the convex hulls seem to be useful for detecting out of distribution as well. So as we see here, the distance to the convex hull for CFAR and MNIST can separate these two relatively well. So for message 2, is that a trained image classifier is defined by its decision boundaries, as we saw in many of the talks earlier on. So a trained model is a classification function that partitions its domain and assigns a class to each of those partitions. And the partitions are defined by the decision boundaries. What's important to realize here is that the extensions of decision boundaries outside the convex hull of the training set are crucial in model performance in its generalization. Which leads me to the message 3, which is overparameterization is necessary but not sufficient to have control over the extensions of decision boundaries outside the convex hull of the training set. So in order to have control over the shape of the extensions of decision boundaries outside the convex hull, we need the model to be overparameterized. And we can prove this for polynomial decision boundaries using the orthogonal system of Legendre polynomials. Here is some simple intuitive example we have. for shaping the extensions. But once we have over-parameterized the polynomial can have very different, and the over-parameterized polynomial can have very different shapes outside the convex hull while still fitting the training set. So picking a polynomial with a specific shape outside the convex hull would require using a specific training regime. So these two, over-parameterization and training regime, in this setting go hand in hand. They work in tandem, which is the message 4. Over-parameterization and training regime work in tandem in shaping the extensions of decision boundaries outside the convex hull of training set. So we, as in the deep learning community, we train a network while looking at its accuracy on a validation set. And this is how we shape the extensions of decision boundaries outside the hull. This can be interpreted as we practice to extrapolate on a validation set, and that extrapolation hopefully generalizes to the testing set as well. But if we are given an over-parameterized model and a training set, merely minimizing the training loss on that training set doesn't necessarily give us a model that would generalize well. And that's the key to another affirmation to the extrapolation idea. So we studied this for polynomial decision boundaries and some neural networks in that same example. I'm going to stop at the conclusion slide in case there are any questions. Thank you very much.
Thank you very much for the nice talk. Do we have any questions for Ruzbe? Okay, thank you very much again, Ruzbe. Why don't we move on to the next talk, which is characterizing high-dimensional representation learning in over-parameterized neural networks. So Arna, I think you wanted to make sure your video permission was working. Is that the case now, or is it still an issue?
I can try. I mean, I can share screen, but yeah, I cannot share my video. But it's fine. That's not a big problem.
I'm unfortunately not seeing a way of giving you permission to share video. That might just be a
that's okay. That's okay, no problem. Thank you so much.
Oh, I think I was just able to help you start video. So let me know if that worked.
Oh yeah, it works. Thank you. Thank you. All right. So thank you so much for the introduction. I'll be talking about our work in characterizing high-dimensional representations and over-parameterized models, and this is joint work with Kumar Krishna Agrawal from UC Berkeley and Dr. Blake Richards from Mila and McGill. So when we talk about high-dimensional representation learning, I think one of the golden gold truth systems that we have is the brain. And if you want to draw parallels from the brain to, let's say, artificial neural networks, which are known to do well in high dimensional settings, one of the key observations that is common to both these systems and very pertinent to the current workshop is over-parameterization. And brains are thought to operate in this over-parameterized regime where sensory cortices operate with over-complete basis sets. So they have an over-complete basis set that allows them to have smooth representations and makes them more robust to noise. Additionally, it offers them a flexibility to match the generative model of the input stimuli. And I'll not go much into the over-parameterization in neural networks, but we all know the double descent phenomena. Another parallel that has recently emerged is followed from an observation in the mice visual cortex, which the covariance between neural activities follows a 1/n power law. What that means is that if we plot the eigenspectrum, that is the eigenvalues of the recorded neural activities, the nth eigenvalue is proportional to n power minus alpha, where alpha is almost equal to 1. And if we try to enforce this artificial regularization on representations in a deep neural network, it actually improves the robustness to adversarial noise. So following up on this, we had two hypotheses. One, that the eigenspectrum of the learned representation is closely linked to the network capacity. To study this, we try to increase the number of parameters or change the network capacity by increasing the number of parameters in a single hidden layer artificial neural network and train it on a supervised learning task and see how its eigenspectrum changes. The second hypothesis that we had was this eigenspectrum decay that characterizes the topology of the learned manifold actually indicates the generalization performance of the model. To study that, we again looked at the trained here single hidden layer artificial neural network and study how its generalization performance varies with eigenspectrum decay. And a loose hypothesis or a long-term goal that we had was we wanted to explore if overparameterization actually favors having this 1/n eigenspectrum, which is observed in brains. So we picked up a very toy task classifying digits on MNIST, and we replicated the double descent phenomena across different label noise settings. But what we also observed is for each of the model here, we looked at its eigenspectrum decay. And what we observed is when we increase the parameters in the low parameter setting or under-parameterized models, if you may, the slope of eigenspectrum was slower than 1, which means it corresponds to a discontinuous manifold in some sense. And as we increase the parameters, it transitions from a discontinuous to a smooth manifold. And for over-parameterized models, what we observe is that the eigenspectrum decays, it gets closer to 1, which is the red line here, which is where the brains are supposed to lie operating. And similarly, we observed how the test accuracy varies with the eigenspectrum, and we observe a very strong correlation across different noise settings. Once again, it kind of points to the fact that eigenspectrum is somehow a good indicator of the generalization performance of the model. With respect to this current workshop, I think it's interesting to discuss some possible theoretical implications. And I think this is what I observe now. What I'll present now is just a tip of the iceberg, and there's a lot of literature that has been presented in the keynotes today. So one thing that I feel is worth mentioning is this eigenspectrum decay that indicates the continuity of the learned representation manifold. So it has been shown that if the eigenspectrum decay is slower than 1, it indicates that the learned manifold is discontinuous, and it's therefore susceptible to noise and stimuli, which basically offers a lower bound on how fast the covariance spectrum should ideally decay. On the other hand, it has been shown that if you have smaller eigenvalues in the representation space, it could lead to serious overfitting in a regression setting, which means that rapid eigenspectrum decay would indicate more eigenvalues that are small in magnitude and therefore hinder generalization performance. This actually offers an upper bound on how fast the covariance spectrum could decay. So overall, these two factors kind of propose a trade-off between a lower bound or between the discontinuous manifold and good generalization. With that, I would like to end the talk, and I'll be happy to answer any questions. I'll just go back to the reference slide in case somebody's interested.
Thank you very much, Arna, for the very nice talk. Do we have any questions?
I have a question. Hi,
Yeah.
thanks for the talk. I was just curious where, if you could explain a little bit more about where some of these observations come from. Are these based off of empirical observations in nature? I didn't quite follow the experiment you did on MNIST.
So the MNIST experiment, I'll just go to that slide. So I think, yes, our work is basically empirical. So this is the experiment that I think you're talking about. So yeah, these measured eigenspectrum decay is empirical evidence in the sense that for each model that we trained here, we looked at the representation space. We plotted the eigenspectrum of the covariance matrix of representations that are learned in the hidden layer, and we looked at the slope of that eigenspectrum. That's what I'm plotting here.
Oh, right. My question was more of the some of these conjectures you had on your final slide, or possible theoretical statements where, we're dealing with
Right.
Sarah robustness, where I was wondering if these are things that have been observed, sort of like the things that Michael Mahoney presented earlier.
Yeah, so I was not aware of like what Michael Mahoney presented, but it was mostly this paper from Dr. Kenneth Harris's lab in Nature. So they present a more theoretical understanding of how the representations actually refer to, like if you learn a continuous kernel from an input to representation mapping, the resultant eigenspectrum decay should be faster than 1. And on the other hand, this paper from Advani, Sachs, and Sampolinsky in neural networks talks about in a single layer neural network regression setting, if you have small eigenvalues, which is again concurrent to the work that Dr. Mahoney presented, it's actually hinders generalization performance. So it's that kind of offers a trade-off that you do not want to have a very rapid decay, but you also don't want to have that decay faster than 1.
Great, thanks.
Yeah, thank you so much.
Great. Thank you very much, Arna. That was a very nice talk. We're going to move on to our next presentation, mitigating deep double descent by concatenating outputs. And do we actually?
Okay, you hear me now?
Yeah.
Okay, great. And you guys can see the screen and the cursor as well, right? Okay, great. Hi, everyone. I'm Qi Han from Rice University. I'm presenting this work in collaboration with John Chen and advised by Dr. Thrampoulidis. The topic is mitigating deep double descent by concatenating inputs. For the time's sake, I will be skipping the introduction of the double descent since we've been here all day. The double descent curve is an intriguing property of deep neural network. And here we are exploring this idea by asking the following questions. The first one is, what is the definition of a sample? Can we expand or squeeze existing data sets, and how this motion affects the performance and the double descent curve? What would be an easy data construction that would somehow challenge the double descent curve? And what is the intuition behind this ablation study? So here we present a very simple way of artificially augmenting a data set. That is by concatenating 2 data so that you can create a data set of size n squared instead of size n. Here, this is a simple definition, and this is a simple example for a vision network. So instead of inputting one image of a number and producing a one hot prediction, here we concatenate or simply stack 2 images and ask for a 2 hot vector as for the prediction. So through this method, we can create a database that is of size n squared, and even larger if you stack more images, and that contains the same information as the original data set, since we didn't introduce anything new. So this deviates from the one hot supervised learning scenario, but this is still remains within the supervised learning scenario. And through this setup, we challenge how we look at a sample. Is it really the size or the number of samples or the information included in the data set, and how we do supervised learning? So our goal is to study the double descent phenomenon under different X-supervised scenarios. And this presentation focuses on variants of supervised classification and how simple data constructions can alter double descent phenomenon. So just to, as a disclaimer, this is purely an experimental study, but theoretical justification is our goal. So using this augmentation method, we show double descent curve results under 2 different settings. The first one is a feed-forward neural network with 1 hidden ReLU layer on MNIST. And then we show ResNet 18 on CFAR 10 and CFAR 100 dataset. So for the different experiment setups, here we consider 3 cases of how we set up a network. The first one is the original way of setting up with inputting 1 image and 1 output image. The second one is simply stacking the same input twice and expecting the same result. And the third setting is stacking two different images and expecting a two-hot vector as a result. So here, those three setups, it's the left, middle, and right, and the top row is loss and the second row is error. So as you can see here, the double descent curve remains the same between the naive setup and the setup of stacking the same image, but the double descent curve is removed on the right, on the last setup. This is interesting because by doing the stacking of the same image experiment, we show that it is not the additional parameters that remove the double descent curve, but the fact of stacking different inputs. And again, we reproduce the same experiment on Restan 18 and CFAR 10 and CFAR 100. Here we explore the double descent curve of two kinds. The first one is the final accuracy of models for a model with different widths. And the second one is the one we've shown before, is the double descent curve across epochs throughout the training. So here, this is a model size double descent. The x-axis is the width parameter for Restan 18 network. And here you can see the double descent curve is not removed, but mitigated. And another thing worth noticing is that the error and loss, the error remains the same, while the double descent curve is mitigated in the interpolation region. And in the bottom, we can see the similar results appearing again in the CFAR 100 dataset. Similarly, we explore epoch-wise double descent, which is repeating the previous setup, but for using x-axis for epochs. And the three lines are three different width vectors, respectively. Here, we can see that, again, the double descent curve is really mitigated in the interpolation region. And this is shown again in the CFAR 100 dataset. So to summarize, we believe it appears possible to manipulate over-parameterization and under-parameterization by artificially boosting the number of samples by concatenating inputs. This is again very interesting because we didn't introduce more information by simply just stacking the inputs. We created a different double descent curve. Although we can build models for concatenated inputs from models, for the standard setting, the double descent curve is shifted in this case. This begs an improved understanding to model capacity, as well as the relation of the bias variance trade-off. Although we create a very large training data set, there is no noticeable underfitting. This suggests we may need to rethink the relationship between underfitting and the number of parameters, samples, and model capacity. And thank you for listening. Please raise your hand if you have any questions.
Thank you very much, Kihan. Do we have any questions from the audience?
Hi, Vidya, if I may ask a question.
Yes, of course.
Yeah. Hi, Kihan. Nice talk. So I had one question regarding the double descent curves with number of parameters. So I think you're comparing double descent with concatenation and without concatenation, right? So in the double descent, in the curve without or with concatenation, as you said, the training set is like n squared, right?
Yes.
I was wondering if double descent might occur at a later point, or.
Yes, I think that's a very good question. And this is something we've been trying to, this is a question, the very good next step for this experiment, but it is very possible that the double descent curve is mitigated because it was simply shifted. but the reason of why that happens still is very interesting for understanding. And also we do see a little bit of performance, like the error increasing, representing what we might think as a double descent. So this is definitely still a question that we don't have the answer fully, but very interesting to figure out.
Yeah, great, thank you. That's really interesting.
Yeah, thank you.
Thank you very much, Kihan. That's very interesting experimental results. So let's move on to our next talk. When is memorization of irrelevant training data necessary for high accuracy learning? And our presenter will be Gavin Brown.
Hey, can you see my screen? Great, excellent. Hi, everybody. My name is Gavin Brown. I'm going to talk to you about memorization of training data. This is joint work with Mark Bunn, Vitaly Feldman, Adam Smith, and Kunal Talwar. So machine learning models contain information about their training data, sometimes lots of information. Our result is that sometimes memorization of almost entire examples is necessary, no matter the learning algorithm you use, and even when many of the details you must memorize are in fact irrelevant to the task at hand. So memorization is sometimes part of the learning process. The description of the k-nearest neighbors model is just a description of the data set. And the dual form representation of an SVM that we all know and love is just includes a description of the support vectors, data points. It's not much of an observation to say that if your SVM is overfitting, benign overfitting, and everything's a support vector, if I give you the model, I've given you a description of the data set. But sometimes this happens accidentally. In striking recent work by Nicholas Carlini and a large group of authors, they showed that the GPT-2 text model memorizes people's personal information, addresses, and phone numbers exactly, among many things that it memorizes. This is, obviously fascinating behavior, but also quite concerning. Before I state our results, I want to disambiguate memorization of the training data from interpolation or fitting that we've talked a lot about today. The closest result to ours is work by my collaborator, Vitaly Feldman, who recently showed that there are settings where any accurate algorithm has to memorize the labels, must overfit or interpolate the data. Our result can be viewed as a significant strengthening of that you really have to memorize a lot of training data or somehow be able to encode some of the training data. In our setting, we're going to have n rows drawn IID from some distribution P. The data will be binary. It'll have D bits per row. It's labeled. We're doing classification. We'll feed the data to a learning algorithm, which outputs a classifier M. And the motivating question is, like, what does M tell us about the data X? One detail I need to mention is that we're going to sample this distribution P. It'll be itself a random variable drawn from some meta distribution Q. So we'll call Q the learning task, and this is known to the learning algorithm, but the distribution P will be like a priori unknown. Before it sees data, it won't know anything. And so for each task in this setup, there's going to be a Bayes optimal learner that minimizes the misclassification error, but necessarily exposes a ton of training data. Our main result is that there exists tasks Q where every data set has a large subset S, a subset of rows, such that first, that there's a lot of information contained in this subset, asymptotically the same amount as the data set, n times d. And secondly, that for every learning algorithm, if the error of the classifier is within some epsilon of this Bayes optimal, then the mutual information between this large subset S and the model M is almost as much as the information contained in S, times a 1 minus f of epsilon factor, where f of epsilon goes to 0 as epsilon goes to 0. And so this like 1 minus f of epsilon means that we're really memorizing entire examples. You think like not just containing a lot of information, but really having to write down addresses and phone numbers. And the fact that we're conditioning on P here means that we're thinking about irrelevant data, stuff that's not useful for the task. So memorizing features that aren't used in the production of the label, or noisy bits. If the model depended only on the task, then this mutual information would be exactly 0. I want to point out this also implies a lower bound on the size of the model. You need a lot of bits to contain a lot of information in the model as well. The learning problems we consider are a mixture of many subpopulations, each of which has its own rules or label. And our tasks, which I don't have time to talk about today, are like stylizations of sequence prediction and image labeling. In our settings, we expect to see many singletons, which are data points that are the sole representative of their subpopulation. And we establish a series of reductions that say if you're accurate overall, you must be accurate on these singleton subpopulations because there's a lot of them. And therefore, you must reveal near complete information about these singletons. And to establish this last step, we proved new information complexity lower bounds for communication, some communication hints. In conclusion, I want to suggest that these giant state-of-the-art models might be actually unavoidable, and they might really need to encode individual inputs at times. And I also want to suggest that it shows new ways in which privacy might be hard, and that maybe the most at-risk populations are the most sensitive ones, where the data is the scarcest. But I want to leave you with hopefully with some optimism. In our models, the hard distribution depends on the sample size n. But if you fix the distribution and let n go to infinity, eventually you don't have to keep memorizing. So maybe once we can gather more data, the problems start to go away. Thank you very much for listening. I'm glad to take any questions.
Thank you very much, Gavin. It's a very interesting perspective on privacy and over-parameterization. Do we have any questions from anybody? Okay, I think we're actually going to move on to our last talk, given that we're slightly over time. So the last presentation for today is going to be on understanding implicit regularization in over-parameterized single index model. And our presenter, again, forgive me, is Maxine Yu.
I forgot to unmute myself, sorry. Let me share my screen again. So can you see the slides? Okay, so today I'm very happy to present our joint work about understanding implicit regularization in over-parameterized single index model in this top machine learning workshop. And this is a joint work with Joran Yang and Jianqing Fan from Princeton University. And next, let me just briefly introduce our motivation. So we know that deep learning can be applied in many fields such as NLP, reinforcement learning, as well as computer vision. But the deep neural networks are always over-parameterized, which can make the problem being ill-posed in the classical statistic perspective. So in the statistics, if one tends to prevent overfitting, one tends to add some explicit penalties such as L1 or L2 penalties. However, this is observed that empirically that sometimes it is observed that some simple gradient algorithms can achieve the solution that can generalize well without adding any explicit penalties. And this phenomenon just originates from implicit regularization of that algorithm, because that means that algorithm itself plays the role of the regularization. So in this work, we'll use high dimensional single index model to understand such phenomenon. So next, let me introduce what is the high dimensional single index model. So for both the vector and matrix case, we assume our response is generated from this model with unknown link F and unknown sparse, a vector or low rank matrix beta star that needs to be recovered. And for model identifiability, we assume the L2 norm or the Frobenius norm of beta star are equal to 1. So our goal is just to recover the direction of the beta star. And this model also involves in some random noise. And for simplicity, we assume we know the distribution of the covariate. And because this is a high dimensional problem, we assume the number of the observations is much smaller than the dimension of the parameters. So this is the basically setting. So the traditional methodology to solve such high dimensional sparse or low rank signal recovery problem is to first leverage generalized states identity and score transformation to construct the loss function and plus some explicit penalties, such as some L1 penalties, such as lasso, or some non-convex penalties, GAL or MCP. In terms of the matrix case, we can use the nuclear norm penalties to solve the matrix problem. However, there are some drawbacks since lasso can always lead to some bias that depend on the dimension, and the non-convex penalties are not that computational efficient. So in our methodology, instead of like adding explicit penalties, we simply overparameterize beta as W hardmark W minus V hardmark V, in which hardmark means the element-wise product, and both W and V are in the same dimension with beta star, which is RP. And because we do not know which entry lies in the true support. And then after properly initializing our parameters, we then run gradient descent with respect to these new parameters, and then run update the beta t as follows for every step. And the main theorem says that if we take our initialization step size properly, then there exists a very long time interval from some logarithm iterations to square root n iterations, in which we can near exactly recover the direction of the beta star. And here the convergence rates are minimax optimal. And it is worth to know that when all the signals of beta star are strong signals, by strong signals, I mean they are beyond the noise level, then we can further get the oracle convergence rate. So the oracle convergence rate means that the convergence rate are the same as knowing the true support. So this is our result for the vector case. And in terms of the matrix case, it is very similar. Instead of adding the explicit nuclear norm penalties, we simply overparameterize beta as WW transpose minus VV transpose. And then after properly initializing, we then just run gradient descent with respect to these new parameters and then update the beta t for every step. So and the main theorem says that if we choose our initialization step size properly, then there also exists a very long time interval from some logarithm iterations to square root n iterations, in which we can near exact recover the direction of the low rank beta star with minimax optimal convergence rate with high probability. So in conclusion, combining with overparameterization and without adding any explicit penalties, we propose a method to use high-dimensional sequence model to understand this implicit regularization phenomenon, and we can achieve similar or even better results comparing to the traditional method with explicit penalties. Thank you very much for your listening, and I'm open to any questions.
Thank you very much, Maxine, for the very nice talk. Do we have any, very quickly, do we have any other questions? Okay, thanks again, Maxine. Thank you to all the speakers for very nice lightning talks, and thanks everyone for the nice questions as well.